All right, so we're going to talk about take this on to partially grouted walls, and this is a more typical case. If I'm not going to put a bar in each of the cavities of the wall, then I will usually only grout the ones with bars in it. You don't have to, but that's a little more typical, especially in this area. So, partially grouted walls are handled in, excuse me, our handbook in section 5.10.2. Just like we did with our fully grouted wall sections, the bars will typically be in increments of 8 inches, right? So we did the one example at 24 inches. We're going to do a similar example, but use partially grouted walls on the next one. The cells are typically grouted at the locations of the steel. And then on the next page, I've actually got these two figures from the handbook on page 205. Um, Basically, this works like T-beams. So I'll show you the picture on the next page, and you can see how this comes to play. So if I've got this scenario, this top scenario, and I figure out where D is, okay, then KD, which is basically the distance to the neutral axis, is going to either be above in this shell part, or it's going to be down here in this piece. If it's above, you basically have that rectangular stress block, right? Awesome. If it is below, then now I've got the part where it's grouted, okay? I don't worry about these little individual pieces that aren't grouted, so we'll typically just take this part, and then you see this is a T-beam design. So just like you learned in concrete class, if the neutral axis is in the web, or in this case not in the top flange, which we call a shell in this case, I get the T-shaped compression block. Um, Most of the time, it's going to be this top case. Just like you spend all that time learning about T-beams in concrete class, a lot of times it's going to be in the slab. The exception is, in bridges where we have some specific cases, but for this masonry case, it's pretty much um, very likely that you're going to have this case where it's in the shell. So if that neutral axis, KD, is less than the thickness of the shell, then basically it's business as usual. I have my two versions here, where if I'm going to use the charts, I've got M equals KF BD squared. Okay, so I can either calculate each one of those or use the charts, go in, find KF, and then figure out what my moment is that controls. If I have a really large block and the bars are placed closer to the opposite face of the compression side, you can have that T-beam situation. We are not going to do an example with that situation. It's not something you're going to remember if you go back and do masonry. You're more likely to get the KD in the face. So I'm not going to go through an example with this. But what I will say is it works similar to what we're used to. I'm just putting, instead of my A's and Whitney stress blocks and all that, it's a little more direct. So I'm going to have, if you look at compression and tension, so I'm going to have a flange part of the compression, I'm going to have a stem part of the compression, and then I have my tension. So compression flange, compression, call it web, but in this case, it's the stem because it's the web, includes the grouted piece and my tension. Okay, so if I want to figure out kg, and in this case, I can look at JD, KD and JD. In other words, the percentage of to JD. Ignore the compression force on the web since it's usually quite small. Okay, so I can actually ignore that piece of the other little webs, but what I can end up with then is dependent on uh, it's a little different equation for K, right? So I can use these equations if I'm in that case. So remember, this only counts if it's the T-beam type case. And then I can figure out my compression force, masonry, and steel um, force and go through it in this way. Okay. So the way to design these would be assume the good case first. In other words, Katie, oops, jumped there quite a bit. Um, Sorry. Oh no, I jumped way far. Yeah, I did. Sorry, guys. Let me see if I can get this. It's gonna. So basically, I'm gonna. Sorry about the scrolling here. This is painful for you. Um, I can find my K and JD. Compression forces, similar to the T-beam equations. If I want to start from scratch and I'm designing a wall, I'm going to assume that case where it's not a T-beam. Okay, so again, I'm going to do a quick example for design. We're going to assume it's not a T-beam, and then we have to check and make sure that KD is less than TF. If that's the case, we go ahead and our design works, assuming that I have enough moments capacity. Okay, so this is a pretty short, basic one. One thing I do need to look at for design is effective width. So you remember doing this when you have T-beams as well, right? We have an effective width. It's a similar type of calculation. It is the least of the three. So you look at center to center bar spacing, 6 times the nominal wall thickness, or 72 inches. So I look at these three, pick the smallest one, and that is the effective width of my T-beam. This is what we would have called it in the reinforced concrete class. All right, you can see the example of kind of what we're talking about, and they have a picture in that handbook that just describes the choices for effective width. All right, so we're going to do this example. I'll do that in a separate video.